So for the integral of x cubed times the square root of x squared minus 1, we're going to think back a little bit to that last problem that we did the other day. Yesterday, where I took that 1 minus sine squared x times the cosine x, and I actually factored the 1 minus sine x, or 1 minus sine squared x into 1 minus sine times 1 plus sine. We had to do some extra work to convert everything into terms of u. Well, that's exactly what's going to happen here. So we're going to start with what looks like should be the u substitution. What does it look like we should sub out?
X squared minus 1.
Yeah. So that would give us du is equal to 2x dx, right? And we don't have 2x dx. We have x cubed dx outside of that radical. But part of x cubed is an x, right? So I could write this as x squared times 2x. And if I put the 2 in, I got to put a 1/2 outside. And then root u, and then dx. Everybody good with me splitting up the x cubed into the x squared and a 2x as long as I put a 1/2 out front?
Yeah.
Perfect. So we now have the 2x dx, but we're left with 1/2 the integral of x squared times u to the 1/2 du. And the problem is we've still got an x squared term in there. And so how do you guys propose we go about removing that x squared?
Could we make more DUs? Would that do anything?
Making more DUs will not do anything good. It'll just make things.
Okay.
Could we find x in terms of u within like the u equals x squared minus 1?
Yes, exactly. So we've got u equals x squared minus 1. I don't need to solve for x. Actually, I can just solve for x squared, right? X squared is equal to u plus 1. And I just need to know what x squared is. So now I do. It's u plus 1. So I'll just make that substitution. 1/2 the integral of u plus 1 times u to the 1/2 du. And now, in order to simplify this down to integrate, we'll just distribute it through. 1/2 the integral of u to the 3/2 plus u to the 1/2 du. Everybody good with that process down to a nice, easy integral that we can deal with?
Yeah.
Yes.
Cool. So now we integrate. So we got 1/2, and the integral of u to the 3/2 is 2/5 u to the 5/2, and then plus 2/3 u to the 3/2 plus our constant. And then we can distribute both the 1/2 through, and we can return the x into, I'm sorry, the u into x squared minus 1. So 1/2 of 2/5 is 1/5, and x squared minus 1 to the 5/2, and then 1/2 of 2/3 is 1/3, and x squared minus 1 to the 3/2 plus your constant. Any questions on that?
No.
Excellent. So we'll do one more of these. Looks very similar. X to the 5th root x squared minus 1. So I suggest we make the same substitution. U equals x squared minus 1 with du equal to 2x dx. Everybody good with that?
Mm-hmm.
So we got x to the 4th, and we'll have 1x left over. If I make it a 2x for my du, I'll put a 1/2 out there. And now I should be able to determine once again that x squared is equal to u plus 1 So what is x to the fourth then? That would be u plus 1 squared times u to the 1/2 du. So even if we don't specifically have an x to the fourth term over there, we can use this u equals x squared minus 1 to figure out what x to the fourth is equal to. Good or no?
Good.
Great. So 1/2 the integral. If I distribute out u plus 1, that's u squared to start with. And then u squared times u to the 1/2 ought to be u to the 5/2. We'll have a plus 2u times u to the 1/2 will be plus 2u to the 3/2. And then we'll have a plus 1, which becomes plus u to the 1/2 when we get that distributed through. Good or no?
Good.
All right, so integrate 1/2 of 2/7 u to the 7/2 plus 4/5 u to the 5/2 plus 2/3 u to the 3/2 plus your constants. I guess I could have written a constant inside of there since I didn't distribute the 1/2 through first. And now we'll distribute the 1/2 and we'll replace the u's with x squared minus 1. So 1/7 x squared minus 1 to the 7/2 plus 2/5 x squared minus 1 to the 5/2 plus 1/3 x squared minus 1 to the 3/2 plus that constant. Good or no? So for this one, we're going to let u equal 1 plus z cubed, which lets du equal 3z squared dz.
Mr. Bachelor, on the bottom for the denominator, it's cube root.
Oh, cube root, sorry, okay. But it's still 1 plus z cubed.
Yes.
Okay, so we're still going to do the same substitution then. So this becomes a 3z squared if we put a 3 there, and we'll put a 1/3 outside. So we end up with 1/3 the integral of 3z squared dz as our du. And now this is 1 over the cube root of u, or u to the negative 1/3. So we'll integrate u to the negative 1/3, which will go up to 2/3, and we'll divide by 2/3, which makes 3/2. So 3/2 u to the 2/3 power plus your constant. And then you just simplify that out. 1/3 of 3/2 is a half. So 1/2 of our u value, 1 plus z cubed to the 2/3 power plus your constant. Does that make sense, John?
Yeah, thank you.
Yep, no problem. Okay, so for this one, you can't let u equal tangent x, because then du is secant squared and you're just left with this random secant sitting around, which is a problem. So we need to recognize that this one looks better like this: secant squared x times secant x tangent x dx. And that way we can let u equal secant x with du being secant x tangent x dx. And we can get rid of all of this and then replace this with just a u squared.
Oh, that makes more sense. Yeah, okay. Thank you.
Yep, so you get u cubed over 3 plus your constant, or secant cubed x over 3. for this one, we want to recognize that the most complicated thing is the natural log. And if we could get rid of that, we'd like to. And we'll hopefully note that the du would be 1 over x dx. And so we've got an x in the denominator, and a 1 is always in the numerator if I want it to be there. So I've already got the 1 over x dx, which is my du. So this just becomes an integral of u squared du. The 1 over x dx, I can put a 1 there if I want. The 1 over x dx becomes your du, and your natural log of x becomes u, so it's just u squared du, or u cubed over 3 plus a constant, or natural log of x cubed over 3 plus the constant. Does that make sense?
Yeah.
Cool. And there's another one on that sheet that's got like an inverse tangent. It's very similar to this one. So I had a lot of people asking about that one during second period, but this should help with that inverse tangent one. It's a very similar idea.